Okay. Good evening, everybody. Thank you very much for coming to our public lecture on a cold, dark night. I'm sure it will be a really worthwhile lecture for you because tonight we have Professor Ian Crawford from Birkbeck, University of London. Ian is Professor of Planetary Science and Astrobiology. And there's a degree course at Birkbeck, so if you've got any questions later, if you're keen on learning a bit more, you want to investigate some courses, then do have a chat with him about that, or with me, because I also did the undergraduate degree there and I was Ian's PhD student. So that's one of the reasons that I'm really delighted to introduce him tonight. Ian is no stranger to the Royal Astronomical Society. He's a very long-serving fellow. He's been Vice President and Secretary. He's winner of the Service Award, and I think he served on sort of many committees and given lots of advice here as well. But his expertise lies in planetary science, so in particular lunar exploration and human lunar exploration, but also in astrobiology. And astrobiology is a developing subject, and it's something that's very exciting for everybody. And so sort of tonight, Ian will be talking about the Fermi Paradox, where are the aliens? So please welcome Professor Ian Crawford.
Thanks, Louise. Yeah, good evening, everybody. So tonight, yes, to talk about something that's interested me for a long time, probably to interest you. Where are the aliens? So this photograph shows the Parkes radio telescope in New South Wales. And it's one of those radio telescopes which is used to try and search the skies for radio signals of artificial origin coming from alien technologically capable civilizations. So this is SETI, the search for extraterrestrial intelligence. And SETI started in 1960 when Frank Drake first used the Green Bank radio telescope to search two nearby stars for artificial radio signals and didn't find anything. So we've now had 60 years of SETI searches, much more sensitive, much more sophisticated searches than Frank Drake's original search. And so far we've detected nothing. So the question is this significant that we've detected nothing? And this is the question that I'm going to try and explore tonight. Now, parts of this talk may seem a bit out there, so just bear with me, and I hope it will kind of make sense in the end. Has anyone heard of the Fermi Paradox? Okay, good. So most people have. So, but I'll explain it anyway. So this relates to a question that the physicist Enrico Fermi asked in a lunchtime conversation in 1950 at the Los Alamos laboratory in the United States, where they were trying to build a hydrogen bomb. And bear this in mind, because if the galaxy's best physicists are all trying to build hydrogen bombs, this in itself might be an answer to the Fermi paradox. But anyway, during this lunchtime conversation, someone pointed out that, bear in mind this was 1950, that there are probably zillions of planets out there. Life is probably common, so there should be life everywhere in the galaxy. And Fermi asked the question, well, if that's the case, where are they? Because if the universe is full of intelligent life, we don't see it. And that was 1950. Since then, Drake set up his SETI project 10 years later, 60 years later, we still don't have any evidence for extraterrestrial life of any kind, technological or otherwise. So is this significant? This is answering Fermi's question. But just to make a point at the very beginning, Fermi's paradox is only a paradox if you go into this and think, yeah, the universe is full of life and we don't see it, therefore it's a paradox. If the universe is not full of life, then of course it's not a paradox, it's just a question. And the answer is, where are they? The answer is, well, they're not there. We don't see them because they're not there. So just bear in mind, really, it's a question. It's only a paradox if you bring to the table a preconceived notion that the universe is full of life. Then it's a paradox that we don't see it. So one of the things that we have learned in recent years is there are certainly a lot of planets. Does anyone recognize this bit of the sky? Nobody recognizes. You can't see this bit of the sky from London, even if it was not raining. This is part of the southern Milky Way. This is the Southern Cross. And this is Alpha Centauri. So this is Alpha Centauri. So that's our nearest star, 4 light years away. But if you look at the back of this, there are zillions and zillions of fainter stars in the background. Of course, they're only faint. They're a long way away. So there are thousands, tens of thousands of stars just in this one image. Now, what we've learned in the last few decades is that planets are very common. The first planet around another star was discovered in 1995. And since then, we've discovered about 5,000. But the statistics of the prevalence of planets and of stars having planets kind of tells us that almost all stars have planets. So if you think that, so that means all of the stars, including all of these faint ones in the background, will have planetary systems like our own, or maybe not exactly like our own, but planetary systems. So if planets are prerequisites for life, then this is a lot of planets. And so this makes a lot of potential places where life could have evolved. So that makes Fermi's paradox even more pressing, because we know planets are very common. Still, we haven't discovered any extraterrestrial life. So anyway, if life is rare in the universe, which I'm afraid I'm going to convince you that, I'm not going to convince you, but I'm going to argue that it might be, it's not because of the shortage of planets. Planets are really common. If life is not common in the universe, it's because of something else, possibly in biology. Just another factoid I would like to bear in mind, if you only remember a couple of things from this lecture, this is one. Since we know something about the ages of stars and the prevalence of planets, we can ask ourselves, how old is the average rocky planet in the universe? And the answer is 7 gigayears. So that's 7 billion years. Now, the solar system, the sun and all of its planets, are 4.5 billion years old. So the average planet, just the average planet, we can't see them, but they'll be there. The average planet in the galaxy is 2,500 million years older than the Earth. This means there has been plenty, if life was common in the universe, there has been plenty of time for biological evolution to occur on this planet. And of course, for it to be much, much further ahead in evolutionary terms than life on Earth, because the average planet has had a 2.5 billion year head start. And there are planets known, exoplanetary systems known, that are 10 billion years, twice as old as the solar system. So in this context of deep time with so many planets, yeah, if life was common on these planets and it evolves to technologies, then shouldn't they be doing things that we would have noticed by now? And so this is the essence of Fermi's question. Right, so this society has published a lot of, its journals have published a lot of papers relevant to this topic. And the Royal Astronomical Society used to have this journal called the Quarterly Journal of the Royal Astronomical Society, which is now superseded by another journal called Astronomy and Geophysics. Anyway, in this paper, Quarterly Journal of the RAS, this what has now become a classic paper in this field by Michael Hart, 1975, published this paper entitled An Explanation for the Absence of Extraterrestrials on Earth. Now, I'm going to, spoiler, tell you Hart's answer is that the explanation is that extraterrestrial civilizations are really rare in the universe, and that's why they're not on the Earth. And I've gradually come to this view myself for reasons I shall argue, but I haven't always felt that. The 14-year-old me would have been appalled to see me standing here arguing that intelligent life is not common in the universe, because I used to be a SETI optimist, and I used to think that life in the universe is common and extraterrestrial life is common. But the problem is, Fermi's question still needs an answer. If it is common, then where is it? Anyway, I want to draw your attention to this sentence from Hart's paper, where he draws attention to something that we might quibble with, but he phrases it like this. A clearly empirical fact of great importance. There are no intelligent beings from outer space on Earth now. There may have been visitors in the past, but none of them have remained to settle or colonize here. Now, let's unpack this a little bit. First of all, it's not strictly, I don't think strictly speaking, we can say it's an empirical fact that there are no intelligent beings from outer space on Earth now. Of course, there is a community of people who think UFOs are evidence for intelligent beings on Earth now, and we can come back to that if you like in the Q&A. Now, I personally don't think there's any evidence that UFOs are visits of alien spaceships on the Earth now, because all the alleged evidence is anecdotal. There is no hard scientific evidence that unexplained lights in the sky are alien spaceships, and there's no logical connection between unidentified lights in the sky and alien spaceships. It's just an assumption that people who want to believe they're alien spaceships make. But even parking that thought, there could be intelligent beings on the Earth now that are hiding from us. We can't say it's an empirical fact that there are no intelligent beings from outer space on the Earth now. A highly technically capable civilization presumably is capable of hiding itself. I think all we can say is hiding itself from us. This is something called the zoo hypothesis, where we are in the zoo. I shall come back to the zoo hypothesis, because it too is an explanation for Fermi's paradox. Anyway, I think this should be rephrased. What I'd be prepared to defend is an empirical fact, is that we see no evidence of intelligent beings from outer space on Earth now, which either means they're not here or they are here, but they're hiding. And then he goes on, they could have been visitors in the past. Now, this must be true. We wouldn't know. If aliens had come into the solar system 2 billion years ago, the Earth was inhabited only by microorganisms at that time. Of course, they could have visited us and left without leaving any trace. But we can be sure that if they did visit the Earth in the distant past, they haven't left any really significant traces because we haven't noticed them. And in particular, we can be sure they didn't take over our planet and use it for their own purposes. Life on Earth has not been extincted by aliens, because otherwise we wouldn't be here. So I think we can be certain that none of them have interfered with the Earth's history sufficiently to interfere with our own evolution, because we would know that. So the question is, we've got this lack of evidence. So the question is evidence of absence of evidence? And this kind of is the question, because logically not. But then if the aliens were doing things that were so obvious, like making us extinct and using the Earth for their own purposes, then of course if we don't have evidence of that, then it didn't happen, because if it hadn't happened, we would have evidence. So anyway, so much of it depends on is the absence of evidence of absence, but ultimately I'm going to try and convince you that it arguably is. So I'm now going to go off on a tangent that you may find, well, not really a tangent, but I'm going to use this word, colonize, because Hart says here, none of them have remained to settle or colonize here. So what he has in mind is no aliens came to this planet in the distant past, and it could be millions or billions of years ago, and they didn't do what certain people, whose names I won't mention, want to do with Mars, which is to colonize Mars. And in the next few years, regardless of whether Mars has microbes of its own or not. Anyway, the aliens have not done that to us, because if they did, we wouldn't have this continuous record of our own evolution, and we wouldn't be here today. So is it possible that some subset, and I'm only arguing it would be a subset, please don't go away and say that I'm arguing that all technically capable civilizations would want to colonize every star in the galaxy. That would be a preposterous, thing to state. What I want to state is that some fraction of them may have. to engage in this activity. It might only be a very small fraction, but even if it was a very small fraction, they could still have visited our planet in the distant past and interfered with our evolution, which didn't happen. I mean, that is the good news. It hasn't happened. The question is, what can we infer from that? So I'm now going to try and convince you that it is possible for some, without advocating that civilization should do this. There are a lot of very interesting ethical questions, which I shall come on to later. But first, I want to demonstrate the possibility that if a sufficiently, let's say, aggressive, or a sufficiently colonizing technological species able to travel between the stars wanted to visit every star in the galaxy, could it do so, despite the fact that the stars are light years apart? And I'm going to argue that, yes, it would be possible. And not only that, it would be possible on a time scale which is long in human terms, but which is short compared to the age of the galaxy. This is the key point, one of it. So here are some green dots. And these green dots meant to represent stars with planetary systems. And we might live on this one, so, or that one. But anyway, sometime in the history of the galaxy, let's say life arose on that one. And life went through its evolution to make an intelligent species evolve that developed a technology that could develop between the stars, something that we are ourselves on the brink of being able to do. But remember, the average star in the galaxy is 2.5 billion years older than the Earth. So this all could have been happening in the distant past if life was common in the history of the galaxy. Anyway, this green dot has invested in 2 starships, and these are the black arrows. Of course, if you can build a starship, you could probably build hundreds. But let's just say it builds 2. So it sends colonies to its nearest neighbours. So in our case, one of those would be, presumably, Alpha Centauri is our nearest neighbour. Barnard's star is our second nearest star, also incidentally confirmed to have a planetary system just recently. Then after the spaceships arrive at the target star, then they find this planetary system. They decide that they're going to set up base in this planetary system, so they colonize it. And then they wait some time until this colony is big enough to send out spaceships of its own. And then each colony sends out 2 of its own, and so on. So then the number of colonies grows exponentially fast. It doubles at every step. And eventually, all of the green dots within some circle will have been visited by starships, but the circle itself will expand outwards into the galaxy at some speed, which is given by the speed of the spaceships, of course, the spaceships, that's the galaxy, but also by the length of time it takes you to reside on one planetary system before you can send off colonies of your own. So you can work out the rate at which a colonization wavefront like this would pass through the galaxy or any other system of green dots like this. And it's a distance, a characteristic distance, which is the distance, the average distance between the green dots. So if these were stars, this might be 10 light years, divided by the sum of 2 times, the time it takes spaceships to travel between the green dots, that depends on how fast you can build up spaceships, and the time it takes each colony to consolidate itself before it can send out colonies of its own. And then you can put in whatever numbers you want into this, but I've just put in some numbers. Suppose you could build a spaceship that could travel at 1/10 of the speed of light. So this is much, much faster than any spaceship we can build today. But on the other hand, it's certainly not physically impossible to build a spaceship that can travel at 10% of the speed of light. And that doesn't push the special theory of relativity doesn't push it at all. So that would then become an engineering problem. A sufficiently advanced civilization might be able to build something that can travel that fast. Although the actual argument doesn't hinge on this being 1/10 of the speed of light. Could be much slower. The conclusion will still be the same. Each colony might take 400 years, say, this is just my estimate. How long would it take a newly colonized planet to start launching spaceships of its own? I mean, 400 years seems a long time in some ways, given that these colonists have arrived on the starship and are unlikely to have forgotten all of this capability. But still, if you just assume 400 years, then this colonization wavefront moves through the galaxy, the green dots in this picture, at a speed of 0.02 light years per year, which means that the whole galaxy, which is a diameter of 100,000 light years, the whole galaxy could be colonized in this fashion in 5 million years. So there are two ways to look at this. I mean, 5 million years seems a preposterously long period of time. So even in human terms, it's not that long. It's comparable to the human evolutionary timescale. But the point is, it's only 0.05% of the age of the galaxy. So this colonization wavefront could have passed through the galaxy in a time that's almost instantaneous compared to its age. And of course, there might have been lots of them. Maybe this star could have evolved technological species and sent out its colonization wavefronts, and this star, and maybe this one. And here are we, say, sooner or later, we're going to get overtaken by one or more of these colonization wavefronts. And if that happened, and it may have happened in the past, then fortunately for us, the colonizers did not interfere with our evolution. I'll come to the ethical answer to the Fermi paradox later. Anyway, at the moment, I just want to demonstrate that here is a galaxy. This is a spiral galaxy. This is Messier 51. Our galaxy would look similar. If this was our galaxy, the sun would be like somewhere here. So here, the sun's already been encompassed by this blue colonizer, and it's about to be colonized by the red one, and it soon will be colonized by the green. The point is, the galaxy, though the solar system is old enough, the galaxy is old enough that planets like planets like the Earth in our own solar system are not really as isolated from the rest of the galaxy as we might like to think. We could have been overtaken by colonizing species from elsewhere in the galaxy many times, because each of these circles could cover the whole galaxy in 0.05%, say, of the galaxy's age. There's been time for this process to have happened multiple times. Now, for very good reasons, colonizing things is not necessarily a desirable thing for intelligent species to engage in. And we can all think of examples in human history where colonization has not been a good thing. And I'm not saying it is a good thing, but it does happen in nature. So here, because, for better or worse, but better from natural selection's point of view, colonizing the environment enhances survivability. Here is an aggressively colonizing species, and it is colonizing my desk. And it is a spider plant. And obviously, you've probably all got spider plants at home. You know what they do. The parent spider plant, eventually, once it's mature, sends out lots of little daughter spider plants on these long stalks. And these are, of course, genetically programmed to be aggressive colonizers. You can look at next time you see a spider plant, you'll see these daughter plants. They've all got their little roots all developed just while they're flying through the air, which is, of course, the equivalent of flying through space. They've developed their roots in anticipation that once they land in a nice, warm, wet plant pot, they will be ready to grow. This spider plant and its colonies would colonize this space of plant pots exactly as the spaceships are colonizing these green dots. You can think of the spider plant in the middle and the green dots as flower pots. So obviously our planet has been a potential flower pot, and it's been there, a nice, warm, wet, rocky, presumably habitable planet for 4,000 million years. And it's been like that, only occupied by microorganisms for 3/4 of its history, but in a galaxy which is much, much older, where biological evolution may have been occurring to develop technically capable of traveling across interstellar space, could have evolved in our galaxy before the solar system even formed. Then our solar system formed, and it's got some nice warm, wet plant pots. And you might think it's some subset, not all, some subset technically capable technological civilizations that inherited a genetic predisposition to colonize the space around them, like the spider plant. Or even like human beings, sad to say, because human beings are also a pretty aggressive colonizing species. Human beings evolved in East Africa, depending on where you think humanity begins, 3 million years ago with or 300,000 years ago with modern Homo sapiens. The point is, since then, we've colonized the entire planet from our cradle in East Africa, even very uninhabitable regions around in the Arctic Circle. So we too, before we just think spider plants are unusual in being aggressive colonizers, human beings are as well. And of course, we do have a technology. The reason human beings can colonize the Arctic is because we invented fire. Oh, we didn't invent it, we learned how to use it, and clothes, and stone tools, and eventually spaceships and nuclear weapons. But I'll come back to that. But anyway, the point is, we have developed a. It's not. It would be wrong to think that technically capable species just won't engage in this kind of activity. Probably some will and some won't. But anyway, so all I've done here is try to convince you, not that all civilizations would engage in this activity, but that it's technically possible, and therefore some small subset of them might. And obviously it's those we don't see. So should we expect to see them if they've ever appeared in the galaxy? But of course, the good news is they haven't. The Earth has never been one of these plant pots. I mean, this little plant pot here might have had its own little plant trying to grow. That would have been like the Earth 2 billion years ago. And then this has been implanted in it, and it's just been exterminated because its life's been taken over by the spider plant. But that has not happened to us, right? This is the good news. It has not happened to us. But then why not? This is the essence of Fermi's question. Why not, if technically capable life is common in the universe? Right, so proposed solutions to the paradox. Well, if interstellar space travel is impossible, then yeah, this is a solution to the strong form of the paradox. It still doesn't explain why the SETI searches haven't found anything in 60 years, because that doesn't depend on interstellar space travel. But it would explain why we haven't had alien spaceships visiting the solar system in the last 4,000 million years if interstellar travel is impossible. And indeed, the stars are a long way apart, so interstellar travel is going to be technically very difficult. But anyway, interstellar space travel can't be impossible because we're doing it. So there is a very nice computer program called Eyes on the Solar System. So NASA, you can Google it, NASA website, Eyes on the Solar System, and it tells you where every NASA spacecraft is at any given time. But if you zoom out, you've got to zoom out from the solar system a long way. It will show you the current locations of these 5 spacecraft, Voyagers 1 and 2, Pioneers 10 and 11, and New Horizons, which are already well beyond the solar system. So these 5 spacecraft are leaving the solar system. This is the solar system schematically here to scale, and this outer blue circle is the orbit of Neptune. So all of these 5 spacecraft are leaving the solar system, and they will eventually travel the distances to other stars. Of course, they don't have passengers. They're not designed to colonize any other planetary system. And by the scale of the galaxy, they're moving. I mean, these are the fastest human-made objects. But by the scale of the galaxy, they're moving very slowly, 16 kilometers per second. So yeah, it would take Voyager 1 77,000 years to visit a planet orbiting Alpha Centauri, and that's our nearest star. Just to point out, though, that even these obviously a technically capable civilization that was serious about colonizing stars around it would probably develop things that travel much faster. Come to that in the next slide. The point is, though, even we are building spacecraft that are slowly traveling interstellar distances. So it seems that traveling to other stars can't really be impossible. And just notice, even at these really slow speeds, even the Voyager spacecraft launched on a chemical rocket in 1977, and the gravitational swing by of Jupiter in 1979 and Saturn in 81 is traveling at 16 kilometers per second. Even that spacecraft could cross the whole galaxy in a time that's still relatively short compared to the age of the galaxy. It would take for the Voyager spacecraft 1.8 billion years to cross the 100,000 light years. I mean, that's obviously on human timescale, an enormous timescale. But it's only 18% of the age of the galaxy. Even with our current chemically propelled rockets, we could cross the galaxy on a timescale that's shorter than the age of the galaxy. I just highlight that because the galaxy isn't quite as big as we might sometimes like to think that it is. And especially not if your technology is able to build things that go much faster than the Voyager spacecraft. So even we, to quote someone whose name shall remain anonymous, even we have concepts of a plan for building things that can travel much faster than the Voyager spacecraft. We haven't built them yet, but we can see the physics would work. We can see a technological roadmap to building things that might travel at 10% of the speed of light. There's a whole, I mean, there are many, many things on sort of that have been on drawing boards. Laser pushed light sails, which is Project Starshot. You can, I'll let you Google it, but the plan would be to accelerate reflective sails, basically reflective surfaces with powerful laser beams to travel at like, well, Starshot thinks it can build things to travel at 20% of the speed of light. You could imagine large rockets. This is a Daedalus concept called Daedalus, a large nuclear-powered rocket to accelerate a payload to 14% of the speed of light. These are currently beyond our capabilities, but we can still see a way of designing, building such things even now. And just remember, the average planet in the galaxy is 2.5 billion years older than the Earth. The average technical civilization in the galaxy, assuming what technical civilizations are common, would be billions of years ahead of us. And yet we can think of ways of traveling between the stars on decadal time scales. And we could probably, you know, if we wanted to, we may not, but if we wanted to, we might well be able to implement some things like this in 100 years' time, which is just nothing compared to the age of the galaxy, obviously. So I'm going to make the point that interstellar space travel is not impossible, and therefore that's not a solution to the Fermi paradox. But you're welcome to push back on that in the Q&A. Proposed solution 2, yeah, this is a much deeper proposed set of solutions, I think. Not all extraterrestrial intelligences will be motivated to colonize the galaxy. Now, that is certainly true. You can't claim that all extraterrestrial civilizations would behave in the same way, because if extraterrestrial civilizations are common, there must be a spectrum of possibilities. There'll be a whole range of different cultures, I mean, different biologies to start with, so hence different cultures, different ideologies. Of course, they're not all going to behave in the same way. So, assuming that everything behaves in the same way, in astrobiology, in this context, has become known as the monocultural fallacy. The fallacy is you assume the aliens are all the same. Well, the aliens are not going to be all the same because they're all independently evolved with totally different histories and biologies. So you can't assume that all alien civilizations want to colonize the galaxy. But of course, I'm not assuming that. I'm just assuming that some subset of them might. And the more technical civilizations have existed in the history of the galaxy, whatever that fraction is, I mean, let's say in the history of the galaxy, there have been 1 million technically capable civilizations have evolved in the history of the galaxy, which is, I mean, that's compared to Carl Sagan and Frank Drake, I think certainly call them SETI optimists. We're certainly thinking, you know, in those lines. But suppose there were 1 million technically capable civilizations involved in the history of the galaxy. Suppose only 1%, about 99% of them didn't ever want to go anywhere. 99% of them were happy to live in their plant pot and not send out any colonies. But if 1% decided to engage in a sort of colonization program like this, 1% of 1 million is 10,000. So even if only 1% of 1 million civilizations were to engage in this aggressive colonizing capability, you know, activity, you wouldn't have 3 circles on this diagram, you'd have 10,000 of them. And that's with only 1% of technical civilizations engaging in this activity, right? I mean, I don't know whether I'm articulating this clearly, but this is what brings the Fermi paradox. This comes to the crux of the Fermi paradox, because if these technical civilizations have been really common in the history of the galaxy, it really becomes, assuming there've been anything like 1 million of them or really large numbers, this then becomes really difficult to explain why none of them not only visited the Earth, but didn't visit the Earth, or did visit the Earth and didn't interfere with the Earth. I mean, suppose we'd had 10,000 visitations in the history of the galaxy. Suppose only 1% of those thought that it would be a good idea to take over this planet inhabited only by microbes, which the Earth was 2 billion years ago. Then that's still 100 of them taking over the Earth. Well, none of them have done that. Right? That's the good news, but then why not? we won't fall into the monocultural fallacy. We won't assume all these technical civilizations behave the same way. But if some subset of them do, then if there've been a large number of these civilizations in the history of the galaxy, there's still, Fermi's question still stands, because we haven't seen any evidence for this activity. Now, I think some subset of these technically capable civilizations there are reasons for some subset of them, maybe much more than 1% if you go through this list, might decide that they're quite happy colonizing the whole galaxy. Firstly, some of them, they have a genetic predisposition to colonize everything. Right? Exhibit A, the spider plant doesn't think about colonizing these plant pots. It's genetically evolved to do it, and it just does it. So can we be certain that technologically capable species wouldn't behave in some fraction of them, say 1% of them, wouldn't behave in the same way? Well, we might like to think that intelligent species are conscious entities and think about what they're doing in the way that spider plants won't, and they may come to some conscious reasons that non-conscious self-replicating entities, wouldn't think of. But even for thinking entities such as ourselves, we can imagine ideological motives. Human history has had many examples of many cultures, and some are aggressive colonizers and some are not. And human history is replete with lots of very bad examples of what happens when these different types of cultures can meet. But if different human cultures have a spectrum of propensities to colonize their surroundings, why shouldn't different alien cultures? Regardless of whether some subset of them develop ideological reasons for wanting to colonize the universe around them, ultimately they're all going to have a perfectly rational reason for wanting to colonize other stars, planets of other stars, because no star lasts forever. So the picture on the right here, this is the Helix, the Helix Nebula. It's in the constellation of Aquarius, and it's 650 light years away. And it's what happens to sun-like stars at the end of their lives. It's called planetary nebula. The sun will be a planetary nebula in 7 billion years' time after it's been a red giant. And by the time the sun becomes a red giant and ejects a planetary nebula, the solar system will be uninhabitable. Now, in the history of the galaxy to date, almost a billion, something like 800 million roughly solar-type stars have become, in astronomical parlance, have left the main sequence and become red giants and ejected planetary nebulae. Now, we now know, thanks to our exoplanet statistics, that all stars are planetary systems. To a first approximation, this star, now represented by a white dwarf in the middle, would have had a planetary system. And 800 million of stars have ended their lives like this in the history of the galaxy. So 800 million planetary systems have been destroyed. Well, if life was common on all of these planetary systems and some subset of this life developed spacefaring capability, then these intelligent, technically capable species around these evolving stars have a choice. They can either stay at home and become extinct, or they can move out to other stars. So some may choose to become extinct, but some probably wouldn't. But then the final bullet point is long before intelligence, technically capable species stop to have to worry about the evolution of their star, they're likely to start to develop the capability to travel between stars just out of scientific curiosity. That's why we're doing these designs, to start investigating planets around stars in their vicinity. But of course, once they do that, they've developed the cat's out of the bag then. We've developed space rockets to study Mars for scientific curiosity, but we're on the verge now of using that technology to colonize Mars with humans. This is a story that will play out over the coming decades. SpaceX is launching its Starship rocket again, 6th test flight this evening. 10 o'clock, right? And Musk wants to colonize Mars. So, but building on, we don't have to agree that's a good thing to do. I think it's not a good thing to do, but a lot depends on whether Mars has life of its own. Anyway, that would be a different talk. But the point is, once you've developed a capability for scientific exploration, the cat's then out of the bag for others to use it to colonize the space around them if they wish to do so. So there are these lists of reasons why some subset, but not all, of technically capable civilizations in the galaxy might want to engage in a galactic colonization program. So there has to be a spectrum, propensity to colonize versus number of civilizations. Let's say we don't know the form of this distribution, but there has to be one. Some will have an average propensity to colonize, that'd be in the middle. Some will always want to never leave their home planet, and some fraction will want to colonize adjacent planets. And it's these that we don't see. But it depends how populated these distributions are, right? But if there were 1 million civilizations contributing to this distribution, and 1% of them were down here, that's still 10,000 would be colonizers, and we don't see them. So Fermi's questions, on the other hand, if there were only 6 would be colonizers in the history of the galaxy, so then technological life is then very rare, of course. Then, of course, if you put 6 random points along this axis, there might not be any here, and we wouldn't see them. And that would answer the Fermi paradox. We wouldn't see them because they're rare. Anyway, I don't have time to dwell on that. Happy to answer questions if we have time later. Proposed solution 3. Extraterrestrial intelligences, because if they start to develop technologies that will enable them to travel between stars, they'll probably develop very destructive technologies as well, and therefore they could all destroy themselves before they break out into the galaxy. And this picture shows the first hydrogen bomb test. This is the Ivy Mike test, 1952. Exactly the kind of thing that Fermi and colleagues in the Los Alamos laboratory in 1950 were trying to build. And as you can see, they've successfully built it. So if all physicists in the galaxy are building hydrogen bombs, right, then they could extinct themselves before they can break out into the galaxy. So this is in principle, that's a solution to Fermi's paradox. But of course, we're falling into the monocultural fallacy. We're assuming that all civilizations that build hydrogen bombs, or could build hydrogen bombs if they wanted to, would actually build them and would actually destroy themselves. And this is implausible if there've been a large number of them, because just as there has to be some distribution of propensity to colonize, there must be some distribution of propensity to self-destruct. Some will self-destruct, others won't. You can't argue, it's implausible to argue that if there had been 1 million technological civilizations in the galaxy, they would all self-destruct. And bear in mind, even if 99% of them self-destructed, you've got 10,000 that didn't self-destruct, that you might expect to find evidence for, and we don't. So I think this, although it's a very common pessimistic solution for Fermi paradox, they all destroy themselves. It's not plausible, because it's falling into the monocultural fallacy that all alien civilizations will behave in the same way. Notice that although we get very pessimistic about ourselves, our human beings, that is, often with good reason, we have lived with this destructive technology for 70 years. We haven't yet destroyed ourselves. I mean, we might yet do so, but the fact that we survived with this technology for 70 years actually shows us there is no automatic. It doesn't follow automatically. Just because you can design hydrogen bombs, you will necessarily destruct yourselves. It would depend on the geopolitics of the society. And some of these societies are probably very different from our own. So I don't think self-destruction is an answer to the Fermi paradox. Solution 4, extraterrestrial intelligences are constrained by strong ethical codes against interfering with primitive life forms. Now this deserves to be taken quite seriously, I think. In the Star Trek universe, this is the prime directive. In astrobiology, it's usually known as the zoo hypothesis, after this paper by John Ball called the zoo hypothesis that was published in 1973. So he's got this very brief abstract. I'll read it. Extraterrestrial intelligent life may be almost ubiquitous. I mean, that's kind of our expectation of it has been. The apparent failure of such life, so that's what we need to explain, the apparent failure of such life to interact with us may be understood in terms of the hypothesis that they have set us aside as part of a wilderness or zoo. So yeah, the aliens are there. The technically capable extraterrestrials are all around us. The galaxy is full of them, as you know, consistent with its great age. But we don't see them because they are deliberately hiding from us. And we must assume this to be possible in principle. If you've got the technology to travel between stars, you must have the capability to presumably remain hidden if you wish to do so. So my colleague, Dirk Scholz-McCoo, at the Technical University of Berlin, and me wrote this paper earlier this year in Nature Astronomy, where we kind of argued that actually the Fermi paradox boils down to, in our view, the zoo hypothesis or nothing. The zoo hypothesis is that we're in the zoo and the aliens are hiding. And the nothing is that they're just not there. That's why we don't see them. And we felt that it probably boils down to one or two of these. Now, here there is a tension. If you dig out our paper, there is a tension in it, because Dirk thinks that life is really common in the universe. And therefore, he needs an explanation for why we don't see it. And the zoo hypothesis provides an explanation. I am a bit less sanguine about the zoo hypothesis because I'm afraid I see it as being yet another example of the monocultural fallacy. If there have been thousands or hundreds of millions of civilizations evolving in the history of the galaxy, and there has been time for that, they're not all going to agree on the same set of rules for the zoo. Some will impose their prime directive, others won't. So why don't we see those that don't or have different rules? So I'm actually, although the zoo hypothesis is my second favorite answer to the Fermi paradox, I'm not sure that it stands up to scrutiny. But I think we can test it. In a sense, we're already starting to test it because we are gradually breaking out of the zoo, right? Here are our spacecraft heading to the stars, and there are going to be many more of them in the coming decades. So gradually we're breaking out of the zoo. So we might trigger a response if we're really in the zoo because we're starting to rattle the cage. Or we might, as we explore our own solar system, we might look for evidence that extraterrestrials, they visited us in the distant past. They've got their version of the prime directive, the zoo hypothesis. They have left the Earth alone, thankfully. But still, they've studied the solar system. They've landed on other places like the moon. So you recognise this from 2001: A Space Odyssey. And no one's really expecting to find an alien obelisk on the moon, but still, you know, we haven't really explored the moon properly or the rest of the solar system. So I think as we continue to explore, this is another possible test for the zoo hypothesis. If the aliens have been here, the Earth's been retained in a zoo, they may have left evidence. Depends how carefully they've cleaned up after themselves. Could you imagine we might find evidence elsewhere in the solar system of ancient visits to the solar system? We just have to look for it. And then proposed solution 5 is, we don't see them because they're not there. So in some ways, this is a pessimistic solution to the Fermi paradox. If you want to believe extraterrestrial life is common, then you know this goes counter to what you want to believe because it would imply they're not there. But obviously, it is a solution to the Fermi paradox. If extraterrestrial technologies are rare or non-existent, so somewhere on this spectrum between rare and non-existent, we don't see them because they're not there. Now, how likely is that? So I've asked the question, does the history of life on Earth provide a clue? And I think it does. This ruler shows a potted history of life on Earth. It's graduated in billions of years. The present is at the top. So 1 billion years ago, 2 billion years ago, 3 billion years ago, 4 billion years ago, formation of the Earth here, 4.5 billion years ago. So we have evidence that there was life on Earth very early on, fossilized microorganisms appearing in the fossil record down here. So that kind of might imply that microbial life arises commonly, easily, in inverted commas, perhaps, on planets that are like the Earth was 4.5 billion years ago, because if it was hard, why did life appear on the Earth so soon? That's, you know, perfectly valid argument. There's a lot of detail here I don't have time to go through, but the appearance of multi-celled animals on this planet is here, 0.6 of a billion years ago. So for this whole span of time, 3,000 million years, yeah, the Earth was inhabited by microorganisms. It was therefore wide open to interference from outside, but seemingly was not interfered with. But anyway, takes 3,000 million years before anything as complicated as a jellyfish appears on this planet, because that's up there. And then once you've got multi-celled animal life, then natural selection has been very efficient in making this very diverse, wondrous biosphere that we have around us, and of course of which we are the beneficiaries because we've evolved from it as a technologically capable species. And all of that's happened right up there. So the relative time scales of the time it's taken on the Earth to evolve from unicellular organisms to jellyfish, let alone anything that's capable of building steam engines or inventing fire or building steam engines or building interstellar spaceships. And it's just taken so long to get to that level of complexity that might indicate that this is an evolutionary, very hard step. And yeah, it took 3 billion years here, but maybe it's so hard that on many planets it takes even longer. And that therefore technically complicated life might be really rare. And of course, that would be a solution to Fermi's paradox. It may not be the solution you want to hear, but it would be a solution to Fermi's paradox. We don't see them because they're not there, because evolving complicated life is really hard. So the first person that I know who advanced this argument, can I ask, who has heard of Alfred Russel Wallace? So Wallace, very interesting guy, the co-discoverer of natural selection along with Charles Darwin. His paper, their joint papers were read probably it was in the Royal Academy, or some room in the Royal Academy, the Linnaean Society, but the Linnaean Society didn't have the building next to us, which anyway doesn't make. Anyway, somewhere on this, close to us, Darwin and Wallace's papers were read out in, I think, 1857. And then Darwin's, or 58, and The Origin of Species was written in 1859. Anyway, the point is, Wallace was the co-discoverer of natural selection with Darwin. And Wallace wrote this book in 1904 called Man's Place in the Universe. And coming from the co-discoverer of natural selection, he's advanced here a very interesting argument, I think, because it's basically the argument I made on the previous slide. It's written in very long Victorian language, but let me read it anyway. Given the evidence as to the number of very complex and antecedently improbable conditions which are absolutely essential for the development of the higher forms of life, so he's thinking of all these biological innovations that had to be developed by natural selection from the origin of life to complex cells to multi-celled animals. These things have had to happen one after the other, and each step might have a low probability. So you multiply all these low probabilities together and you end up with a very low probability of having anything like human beings evolve as a result of natural selection at the end. So he says, the total chances against the evolution of man or an equivalent moral and intellectual being, so these would be the intelligent aliens, well, he thought it was very small. Now he picks this number completely randomly he thinks it's a very small probability. He has no idea what it is, but he thinks it's 100 million to millions to one against. This number has no special validity. He just thinks it's very unlikely. Let's say 1 part in 100 million that we could evolve intelligent animals like humans by natural selection. But if he was right, this would make intelligent, technologically capable species very rare in the universe. And so it would answer Fermi's paradox. Who has heard of the Drake equation? So here is Frank Drake with his equation that he wrote in 1961, I think, to try and estimate how many civilizations he would expect to find with his SETI survey. And then, as many of you will know, N here is the number of technologically capable civilizations, and he's worked it out as being the product of all of these things multiplied together. So the rate at which stars form times the fraction of stars with planets. Well, we now know that's about 100%. So the fraction would be about 1. Of course, he didn't know that in 1960, but we know it now. Planets are common. But then you've got to multiply these planets by the fraction on which life evolves, the fraction of such life that becomes intelligent, the fraction, whatever that means. We'll have a discussion on that. Times the fraction of this intelligent life that develops technology. And then you have to multiply all of these fractions by the length of time a civilization lasts, the L at the end. And you get an estimate for the number of technical civilizations in the galaxy. So Drake and Sagan and others were optimistic about life in the universe. And there is the most optimistic solution you can do to the Drake equation is to put all of these factors as 1, because 1 means 100% probability. 100% of stars have planets, 100% of those planets evolve life, 100% of that life evolves intelligence, 100% of that intelligence evolves technology, right? But you can't get more optimistic than that, because these numbers can't get bigger than 1 as they're fractions. So the most optimistic solution you can have to the Drake equation is the number of technological civilizations in the galaxy at any given time is about equal to whatever you think their lifetime is, measured in years, if you've measured the star formation rate at the beginning in stars forming 1 per year. So sketchy optimists like Drake kind of like this solution, because we don't know how long a technologically capable civilization would last, but let's say it would last for 1,000 years. Then there'd be 1,000 civilizations in the galaxy. The nearest today, the nearest one would be about 3,000 light years away on average. And SETI searches are not really sensitive to technologies at that distance. So if you're a SETI astronomer, you can still be optimistic and go to bed at night thinking you might wake up the following morning and there might have been a SETI detection, because if the nearest one is 3,000 light years away, it's just on the boundary of current detectability. But it has a serious implication, this. In order to get all of these factors equal to 1, what you've done here is you've basically set the rate at which civilizations evolve in the galaxy at 1 per year. The galaxy is 10 billion years old, 10 to the power of 10 years old. If technological civilizations appear at the rate of 1 per year, I mean, there might only be 1,000 of them today, but if they've been appearing 1 per year, lasting for 1,000 years each, in the history of the galaxy, there have been 10 billion of them. 1 star in 10 would have hosted a technological civilization. And this then, I mean, I just think it's implausible. I just don't think you can reconcile that with the Fermi Paradox. So this is, I've only got 1 more slide after this to the end. But I just want to show what happens if you're as pessimistic as Wallace was. Wallace's fraction of a probability of evolving intelligent life from simple life, if it was 1 part in 100,000 million, 1 part in 100 million million, which is his guesstimate, that's the equivalent to putting this fraction in the Drake equation to 10 to the power of minus 14. And even if everything else was as optimistic as you can make it, the number of extraterrestrial civilizations in the galaxy at the present time would be 10 to the power of minus 14 times their lifetime. If you think their lifetime might be of the order of 1,000 years, then well, who knows, really, because we've no idea, but if it was, then the number of civilizations in the galaxy today would be 10 to the minus 14 times 1,000, or 10 to the power of minus 11, which would be 1 over 100,000 million. So what does it mean if there are 10 to the power of minus 11 civilizations in the galaxy today? I mean, it means you'd have to look at 10 to the power of 11 galaxies, 100,000 million galaxies, and you would find 1. And 100,000 million galaxies is about the number of galaxies in the observable universe. So there'd be 1, and it would be us. Just by having this number as pessimistic as Wallace thought it might be. So we can obviously you can play with these numbers. You don't have to agree with these numbers. But if the probability of evolving technically capable life is anything like as unlikely as Alfred Russel Wallace thought it would be, yeah, this is the answer to Fermi's paradox. We don't see them, and they never came here because there aren't any. So conclusion. So of course we don't know any of this. Of course, speculation really. There was another eminent astronomer, physicist, scientist. Well, actually, the person who first coined the term scientist, William Whewell, wrote this book about life in the universe in 1853. Notice this is 5 years before Darwin published The Origin of Species. Anyway, he wrote that the discussions in which we are engaged belong to the very boundary regions of science, to the frontier where knowledge ends and ignorance begins. And the sad truth is, despite all the progress in astronomy and biology and other sciences in the last 150 years, we still don't know the answer to Fermi's question. We still don't know how common life is in the universe. We're still at this boundary where knowledge ends and ignorance begins. So I think the only way to make progress is to explore the universe around us. Ultimately, I think it's an empirical problem. If we explore the universe more in greater depth, we will get answers that will help inform our possible solutions to answering Fermi's paradox. So we should be exploring our neighboring planets. We should be exploring Mars, for example, because if we find life evolved independently on Mars, that at least will give us some constraint on the earlier term, some constraints on the fraction of planets on which life evolves, because currently we've only got one example. But we search the solar system for other examples, we'll be able to constrain that. I made the point earlier, we might look around the solar system for alien artifacts. Doesn't cost us anything to keep our eyes open as we explore the solar system. We should continue building big telescopes to look for biosignatures around other stars. This will at least tell us whether life is common, even if it's not technically capable of life. And of course, we should continue the SETI searches because, one day we may get a signal. We may all wake up tomorrow morning and there's been a detection. And then that's kind of answered Fermi's question for us. So we should all we can do is keep looking. So basically, my ultimate, we don't know the answer to Fermi's question, but to get an answer, all we can really do is keep exploring the universe, and eventually I think we'll probably find one. Okay, thank you. I'll talk to you.
Thank you, Ian. Thank you very much. Has anybody got any questions? Okay, if you can just hang on, wait for the mic.
So sorry, I'm acting around. I'm happy to stay as long as anyone wants for questions. I'm not going to run away, but at some point, Louise has to close the building. Sorry.
Stimulations.
Yeah, what?
Possibility that at the time ability there's a signal. So maybe they obviously went maybe the water and the room finally areas change for the signal. So if you can kind of imagine the interest of people in the place, really it was pointing down this signal to neutral stay for kind of the instant directed to us.
Yes, I know. Yes. Okay, so if I can try and answer it. So for people who didn't catch the question, yeah, having made the claim at the beginning that SETI hasn't detected any radio signal, I think SETI has not detected any confirmed extraterrestrial radio signals of proven artificial origin, but there have been candidate signals. So there is this signal, the so-called WOW signal, from I've forgotten the year. 78, I've forgotten, we can Google it, the WOW signal, where a radio telescope in the US did detect a strong radio signal of unknown origin. The problem with the WOW signal, though, yeah, it happened once and it's never been seen again. So it can't be confirmed as an alien signal because it's never been seen again. And nature has its own ways of making sudden radio bursts that might mimic artificial transmissions. So, but you are right. We could, in the history of SETI, there are a couple of unconfirmed signals that might turn out to be alien transmissions, but have not been proved to be so. So I think what I said still holds. There is no unambiguous detection of any radio signal of alien origin. But yeah, buried in the data, there are unexplained radio blips, and maybe some of them will turn out to be alien signals. But the point is, it doesn't really address Fermi's paradox in its strongest form. It really would be extraordinarily, in order for a radio telescope to detect a signal from an alien civilization, they and us have to be existing at the same time and close together in galactic terms, let's say 1,000 light years or so. So the probability of that, in order to have two civilizations existing at the same time, close together, this is an extremely unlikely situation unless these civilizations are very common. If they're very common, though, it invokes all the other problems. The deeper questions of Fermi's paradox is, what were they all doing in the past? What were all these technical civilizations doing 1 million years ago or 1 billion years ago? So something still doesn't add up there, which is why I'm personally pretty doubtful that the WOW signal is going to turn out to be an alien signal. But who knows? All we can do is keep looking, and eventually we may find such signals. No, that's true. I think that's only partly true. So, of course, we're assuming the civilizations might be wanting to communicate by radio. They might be wanting to communicate by lasers, as you say, or other things. Actually, I think we do have the capability to detect powerful laser pulses coming at us from the sky, because optical telescopes are, very sensitive to sudden bright lights appearing in the sky. But the deeper point remains. It means that the transmitting civilization doesn't really matter whether it's transmitting with radio waves or lasers or neutrinos or gravitational waves, anything. For us to detect the signal now means that they are coexisting with us in time. And that is a very unlikely situation unless they are very common. But if they are very common, then we've got all the other aspects of Fermi's question that still require an answer. If they're very common, they have been very common for, millions or billions of years, then where are they? Why do we see no other evidence for them? So Fermi's question still remains, I think. But that doesn't mean we shouldn't open our minds to doing SETI at other wavelengths. I mean, of course we should. It doesn't cost us anything to look. We should keep looking.
We know that it's quite common now. How common are planetary systems like the solar system? So you're looking for, say, a population on a star that is probably planets everything around whether you're looking for what to disrupting your orbit or stable risk and binary stuff. All sorts of things that make the solar system not unique, but in a prime position for life.
So I think only a subset of planetary systems are going to be close analogues to the solar system, with planets within the so-called habitable zone, which is the distance from the star where liquid water might be stable and where our kind of life might evolve. But of course, we're making a bit of a prejudicial assumption here by assuming that life, or even intelligent life, would have to evolve in a planetary system like our own, because there may be many other possibilities. But I think in answer to your question, probably 1 in 10. So probably the current estimates are like 10 or 20%. So probably all of these stars have planetary systems. Probably like 10 or 20% have rocky Earth-type planets within the so-called circumstellar habitable zone. That's still, I mean, it's cut it down by a factor of 10, but of course it still means there are billions and billions of such planets in the galaxy. But I think this too is an empirical problem. I mean, what we need to do is having gone to the first slide and I have to get to the last, we are on the cusp of being able to study these exoplanets through building, large telescopes like James Webb Space Telescope and its successor telescope. So we are on the cusp of being able to develop astronomical instruments that will tell us much more about the physical conditions of planets orbiting other stars and how common planets that are really analogous to the Earth really are. So that too is an empirical problem. And I think the good news is in a couple of decades or so, we're likely to have a much better answer. But my gut feeling is, yeah, probably 10%. So that it's not really enough to, if it was like 1 in a million, if only 1 in a million exoplanetary systems were going to be amenable to harboring the evolution of advanced life forms, then that would start to become a possible solution to the Fermi paradox. Yes, it would. But if it's a 1 in 10, it's not really made enough of a dent in the problem. Doesn't mean that it's not part of the answer, though. I mean, most of these answers are not mutually exclusive. Planetary systems like the solar system could be rare. And in addition to that, even given a rare planet, the evolution of life might be rare. All of these things might be rare. And then, as Wallace argued, you add up all of these rare things and you end up with not much intelligent life in the universe. And that is consistent with the fact we don't see it. So it is an answer. It would be another answer to Fermi's paradox, yes, or part of an answer to Fermi's paradox.
Ian, we've got a question
online. Okay.
Oh, hi, Professor Crawford. This is Lucinda here. I just wanted to let you know we've had over 100 people join us online on Zoom and YouTube for tonight's talk.
Hello,
I have
everybody.
quite a lot of questions, but I'm going to try to combine them together. There's one around, if ETI has star travel, why would they limit themselves to the primitive communications method that radio is? And someone else also asks, how would we expect to detect spread spectrum encrypted laser point-to-point, not deliberately aimed at our way, quantum communication? So, how would they even be able to, how would we be able to hear them with our primitive communications, essentially?
So I think part of that goes to the zoo hypothesis kind of argument. Of course, if they're encrypting all their communications and hiding their signals to look like natural phenomena, then we wouldn't notice, of course. But that's a solution. We don't see them not because they're not there, which is what I've kind of argued. We don't see them because they are determined not to be seen and they're deliberately hiding. So that is that is part of the zoo hypothesis solution. Yeah, the zoo hypothesis or nothing. I mean, I agree. If they're hiding their transmissions, we won't detect them, even if they're there, of course. So that is a possible answer. But I just want to come back to the point about, and so if the first question, yeah, why would a technology that can travel between the stars restrict itself to communicating by radio? Well, of course, it wouldn't necessarily. But the point of the Fermi paradox is it wouldn't need to, because it could have been representatives of that species could have been here in our solar system 2 billion years ago without giving any thought to communicating with us or not. But the fact is, we've got no evidence that if they were here, they didn't interfere with us. This is the real depth of the Fermi paradox. And really, it's, in a sense, SETI, and whether the non-detection of radio signals or laser signals or any other kind of signal, it's kind of a red herring. The real depth to the Fermi paradox is in what was going on in the history of the galaxy. If technological civilizations were common, what were they doing 1 billion years ago? Not what are they doing today? So anyway, I don't know whether that answers the question. But...
yes, I think so. And some people were asking questions about, if we get a signal, wouldn't it have taken place in the past? And how will we know where to find them?
Oh, yes, so it would have taken place in the past, but not by much in the past, right? On the scale and age of the galaxy, then yeah, if we just detect a signal from Alpha Centauri, it would have been 4 years in the past. but 4 years is neither here nor there, really. But then neither is 100,000 years. So even a signal, so here we go. So suppose here's a galaxy again. Suppose it was our galaxy, and I don't know whether people online can see my laser pointer. Perhaps I should use the mouse.
They cannot, unfortunately, but if you could
Okay,
describe
that's fine. I can use the laser pointer in PowerPoint.
or the mouse, yes.
Suppose we are here, and someone is the other side of the galaxy transmitting to us. Then yeah, of course, we'd only receive that signal 100,000 years later. But it kind of doesn't make any difference because the galaxy is 10 billion years old. 100,000 years is neither here nor there, really. All that means that we receive a signal from 100,000 years ago. All that means is we could never reply. Well, we could reply to it, but we'd never be able to have a conversation with the people sending it because the round trip light time would be 200,000 years. So we could never have a conversation over these distances. But the fact the signal would have originated in the past, it's the very shallow past, at most 100,000 years, which is such a small fraction of the galaxy's age. It's almost the present.
Clearly, this is a very interesting talk for many because we have so many questions coming in, but I am conscious that it is 15 minutes past 7, so I'm going to leave it to Louise for now. Thank you so much, Professor.
Okay, thank you, Lucinda. Thank you.
Yeah, thank you, everybody. I'm sorry we've got no more time for any questions, but it's 7:15, and so I think we need to leave it there because we need to lock up the building. But can we please thank Professor Ian Crawford once again for a really interesting talk. Thank you.
Thank you. Okay, was you ready? Oh, was it? Okay, maybe I got clearer the second time.
You probably done it.
It took me 5. Yes. It took me 5 minutes longer though. But anyway, yeah.
Right, great. Thank you.
Okay.
Someone has like today to be very well back from Oxford as well.
Yeah, it's a bit stodgy, isn't it? Because it's our pattern. It's very much as a 10%. So, I actually think that with the formats and components start very from not a big and you've been making things where making the future television